Hello, good evening. It's a pleasure to present to you all, dear students, and Dr. Zhu, the course projects that I have chosen for the Computer Integrated Manufacturing class, the INN 5345. I'm a doctoral student at the Industrial Engineering Department, and my project is titled Steering Mechanical Development Proposal for Semi-Electric Stacker. So as the title implies, it's basically a steering mechanism in a semi-electrical stacker. This semi-electric stacker is a very well-known product that basically, if we can just jump into a photo picture that you could just see the semi-electric stacker, so you could know what I'm talking about. So this is basically a device, a product that usually used in many manufacturing facilities. This semi-electric stacker is used to pick up and place miscellaneous loads. These loads, where the lifting of the load is usually automatic through a push-pull of a vehicle, but the push and pull of the vehicle is manual, but the load itself, when you raise it up and down, it's automatic. So it's considered one of the top-selling products in its industry, and has a very wide range of handling loads, different types of loads. Of course, there are some specifications for this semi-electric stacker that we're talking about. We will discuss that as we go along in this discussion. So the management of many manufacturing companies are always trying to improve this product from a design perspective, from some other parameters, like what we have studied in the class, to design for X parameter. And this parameter X can be anything. Can be manufacturing, could be assembly, could be commissioning, could be for costing and other reason. What we will focus into this presentation and this project is on the design for manufacturing, DFM, and design for assembly. And this product, as you have seen, we are not building it from scratch. It's basically to re-engineer some products that are in the market and try to see what are the problems they face with this product, and what our design for assembly or design for manufacturing will contribute to this product. And of course, we are utilizing CREO and CREO manufacturing as part as our main core objective in this course. So the present project will develop the design for manufacturing, DFM, design for assembly analysis, and this will eventually have to show how our design is going to reduce the maintenance and repair service, is going to overcome some of the problems that they have already in the industry, especially the wheel wear, and we'll talk about it more in details. We will also develop some manufacturing improvements, and we have to show this with some real calculations, so you can really feel the changes that we are introducing for this design. We are going to make also some improvements that will decrease the wheel failure, that as reported by many surveys and many manufacturers about the problems they face with this product. So this is the semi-electric stacker as we have showed before. Now, our main focus in this project will be about the steering system design, or the steering assembly. And this steering, as you see, it's the lower part, right where the wheel is. As you see this stacker, it's exactly where the wheel is. Now we take a more clear look to this steering system. As you see, it consists of three main parts. This first right wheel assembly, and there is the pivot pin assembly, and the left wheel assembly. And we want to see, and this is just a regular CREO drawing I produced. Everything that you see in this presentation, every single part, every single drawing, it's not something that was taken from a catalog or from some brochure or anything. This is completely built, drawn, designed, and manufactured using CREO 2.0 and CREO manufacturing as taught in this class with Dr. Zhu. So it's mainly these are the three things we're looking. So this is the plate that it's called the load plate, and these are the three sub-assemblies that will structure this is a summary of what I have done. It's just a snapshot, screenshot for my working directory that I'm working on for this project. I have produced and created 80 CREO files, 80, that consist of 18 assemblies. Of course, when I refer to assemblies, I'm referring to assemblies and sub-assemblies. I have also 11 CREO drawing, sheets that was created as part of the process, and 51 part files for every single piece in the actual versus the redesigned part. So we will show what is actually now available in the market and what is the change to it. So and we have, of course, our change has to show really. And this is, before we get into more details, we will show also a picture. I have showed you the actual design photo just 1 second ago, and which is here. Actual, you see, if you see the title, it's the actual steering system. You look at it, you may not see that much of a big difference from the redesigned one. If I go to the redesigned one 2 sheets after, you will see there are some kind of serious changes happened in each of these sub-assemblies: the pivot pin assembly, the left wheel, and the right wheel. And let's do some quick comparison here. These are this is my approach when I try to present something, especially when it comes to any project. I wanted you to see the what I am basically was able to reach at, and this almost like a conclusion that will show you the different sub-assemblies and assemblies I have worked on. So I have taken the right, left wheel and the pivot and put them in one chart, in one slide: actual design versus redesign, and that's what and the corresponding drawing. And you may look to the drawings, you may not see much of a difference, and that's what we will explain here, what is really happening in terms of each of these parts, and how did we create a new or re-engineered this part to take into consideration assembly and manufacturing. Here's another exploded view of the right wheel assembly, and that shows you any right wheel assembly. This is the wheel part, and this is pen. It's a load pen. You see the sprocket with some casting here. That's the new one, and here's the actual one. Also see wheel, no changes to the wheel, nothing. It's like, look to the shape of the pen here on the right, and look to the shape of the pen here. That's been redesigned, and we'll tell you why this has been redesigned. And look here, if we do even a cross section for the redesigned one, you see how the red pen here, load pen, it's showing with a cross section, and we'll tell you why this pen is better than this pen. And we'll also look at this part here. It's called the bracket. See how the shape of the bracket, like it's a kind of a irregular shape. You see this compared to this shape. Look at this bracket shape, and that shows you also some work done here and manufactured differently. So when you see a change in the whole part design, that means there's some design changes that happen to this part in a manufacturing part. Look at this blue casting here. It's all one piece. And look here, we have a bearing. We have a bearing here. So these three parts here, like you see this, the difference between the right hand side actual design and the redesigned, it's just this bearing bush. It's all one piece now, one casted piece, and we'll show why is that. So this is another thing for the left hand wheel assembly that shows you the difference. See the blue casted bearing, one piece, and here's 3 pieces welded together. and that's also something we'll explain more. Another exploded viewpoint of the right wheel assembly. You see, this is the right hand side. This is just to give you an idea where are the changes happening. See this blue piece here compared to 3 pieces here, the green and the yellow and the gray. This 1, 2, 3 replaced by one single casted bearing bush here. See, this is a bearing set here, consists of 3 pieces on the right, which is the actual, and those all 3 pieces are welded. Here's just 1 piece. Look to the pin shape, as we have mentioned before, different. Look at, so, and we will discuss the, so this is actual versus redesign. Look to the first part that we're talking about, which is the, here the first, the casted bearing bush. See how this drawing shows both actual and redesign. And if you, the blue is the redesign, which is here, this left side, left hand side, and there's the 3 parts here. See, 1, 2, 3. I'm replacing those 3 parts with 1 part casted, and that you could tell what's the result of that. Less number of parts, less machining, less operational labor, less removal of material. All that thing is contributing to your design of assembly and design of manufacturing. So this is two things here involved, that you have reduced the number of parts, but at the same time you can, and we will show the advantages of this. And here's the drawing corresponding to this first part. Now coming to the loading pen, the actual design, you see how it's cylindrical? That requires a very tricky alignments to put it in place. It's not easy to have just one straight diameter falling into some like section. If you remember here, if I will show you more, but if you go back here, if you remember putting the pin, you see the pin here in the middle. This in the middle shows you how the loading pin has to be aligned, and you see here the spacers, it's in pink color, and the pin that will show you why I have chosen my load pin to be this shape compared to this, which can be much easier in assembly also compared to this one, and that's also shown in the drawing. That's another more clear picture that shows the mounting of the load pen. You see here the left hand side is the redesigned, the right, these are cross sections using CREO. That shows you what is my existing situation right now, the actual design compared to the redesign. You see how it's the shape. It will be much easier to place this pen into this assembly compared to something that is considered to be a very straight diameter with some spacers here that can be really hard to assemble and align. And another look for an exploded viewpoint of the pivot. Now there's a pivot pen. You see the difference between the actual design and the redesign. The actual, you can see how many bolts here, 1, 2, 3, 4 compared to 2, and you also see here 4 washers and 4, you see this number of parts here all reduced to 2, and the hole here is no longer just a straight hole like this. This is almost like a countersunk which can be screwed in. So these types of screws are different than these types of bolts. So that means the shape of the hole and the screw is something, so the mounting here is completely different with much less number of parts compared to the actual design. And we will tell later that this change is not impacting the rigidity of your part, and we will talk about how this is not really harming your product or the stress or load distribution on the plates, and that's something we will explain. That's another look here that shows you all the parts designed, actual versus redesign. You see here again the number 4 of bolts here, 2, and we have again these load pins compared to these pins. The shape of this bracket, you see this bracket compared to this bracket, straight like with this one, and this is important in how that would contribute. So this is the left hand side is the actual, and this is the redesigned. With this, that will make me comfortable to tell you that you could see some of these major differences in the number of parts and some parts that are being completely remanufactured. Now let's talk to in terms of numbers. And let's just show and of course all this been laid out in details in the report. Now we have a comparison between the actual design here compared to the redesign, how the number of parts has changed. The load plate, which we have discussed before, which is this one, the gray one in this color, the load plate is 1 and 1, no changes, same one. Right hand wheel assembly with the sprocket and this you see on the major drawing, it's basically we started with 24 parts, I reduced them to 17 parts, and that's by counting every single bolt, washer, everything. Left hand wheel assembly from 23 parts reduced to 16 parts while still achieving the same objective. The pivot pin assembly, which we have said that this is the top here, you see here, that's called the pivot pin assembly. The pivot pin assembly from 20 parts to 11 parts. So you're talking about 68 versus 45. And of course, you would know immediately reducing the number of parts, meaning time taken, machining, fabrication, welding, everything will be reduced. And that will be also calculated in our study here, just to make sure that we really have sense of the numbers. And here's another chart showing the redesign versus the actual design, how the total final assembly was reduced, you know, as we have mentioned from from 68 to 45. So 68 for the actual blue and the redesigned in the dark. And here's some assembly time also saving. You see also the time that was also calculated. Load plate, there is no time change. Assembly, I'm talking now assembly time, meaning putting things together. The plate is the same. The pivot pin assembly, which was reduced from 68 seconds, that's time taken to put this pivot pin assembly, compared to 44 seconds. Right wheel assembly from 53 seconds to 31 seconds. Left wheel also wheel assembly from 53 to 31. So you're talking about 174 versus 106 seconds in assembly time saving alone. Assembly time in steering assembly also put in chart here for simplicity, just show you in every single stage from pivot to right wheel to left wheel assemblies and sub assemblies, that shows you what's the time saving in assembly time. Here's other parts which I have discussed in brief before about the design for manufacturing parts. What are these? When we have spoken about the design for assembly, which was mainly about reducing the number of parts and doing also some design features that would make the assembly time faster, like the load pin, as I told you how I reduced the alignment time. The actual design here compared to the redesign in the manufacturing side and manufacturing analysis, you can see the bearing bush here. As I have mentioned before, these are 3 parts, 1, 2, 3, compared to 1 casted part. So that means it's much less time, more reliable, because here each of these 3 are connected through some welding, and that welding, you know, it's a cost and time and labor, and that's something that has changed for this part. For this bracket, which is one of the parts that we will focus more on, the CREO manufacturing and structure a CNC computer programming or program that will do this part. So you see the wheel bracket, why this design is better and how this is contributing to the load and stress applied to this stacker. That's something we will discuss. And here's the wheel bracket weldments also, that shows you the actual design compared to this design. After you put the bearing bush on your new bracket, see this new thing, compared to the old one, much less welding and also better distribution of load. And we will also talk about that in the coming. Here's more clear picture more on the bearing bush weldments, which is, we said, 3 parts welded compared to the casting parts. And I have provided in my appendix in the reports how did I calculate the cost associated or compared redesign to actual design in terms of what? Welding. It's like or fabrication cost, the way you fabricate a casted part compared to these 3 parts together. And again, comparison of the wheel bracket. You see the brackets here, how it's shaped compared to this just one side and one side. It's 2-sided a very simple, straightforward bracket compared to this bracket, and we'll tell you what will be the difference. And in cost too, the cost of fabrication, you have to, dear students, we have to distinguish here and be careful. Manufacturing and fabrication needed for your design is something could contribute very a major time and cost, and that's something that can or have to be all the time revisited by the engineers from time to time. Here's some also drawing showing the welding of the three parts. You see where the weldings with this special sign, the welding sign, that shows you there's welding here, welding here. From the geometry, I was able to calculate the welding distance as per the actual, which is the left hand side here, and compared to the redesign. In the redesign, I'm just welding the casted part, bearing bush, to the bracket. You see, much less welding needed. Look to the cost difference between all these three parts, actual versus redesigned, from $3.87 almost compared to $1.69. That's the cost per unit for the welding cost for the difference between actual and redesign. Here's another numbers comparison of machining and welding cost. Also, the way I was able to calculate this machining cost was all provided in an appendix in the report that will show, based on the geometry and based on the unit, the cutting unit with the material per all the data that was provided to me by some existing data for market data for the machining cost and welding cost. I was able to collect and compare this machining cost for the redesigned for both welding and machine. On the top table here, you see the top table, the redesigned, $12.96 for the machining and $1.69 for the welding, compared to $30.59, and the details of the calculations are also provided, but we may not have too much talk about it here in this presentation. Design for manufacturing, again, cost comparison. I have combined now all the parts being manufactured and fabricated, machined, drilled, all the aspects of machining. I have put them in one table. Shows you $35.46 for the per unit compared to $14.65, and that's a chart reflecting that difference in cost for machining and fabrication welding. Now, here is the part considered for by CREO manufacturing I used, and I have showed the this bracket and the dimensions and what is basically happening to this. What's been happening, we applied, of course, as part as we have seen the CREO manufacturing assignments that we have done in this course with Dr. Zhu. We have profile milling and drilling that is achieved for this bracket. All what is done is it's a piece of metal that we applied some profile milling and we applied some drilling for this hole that we, and here's a summary for the process. I have basically started with some raw material. I applied the raw material cutting, machining for the secondary process. It starts from a basic to machining, some heat treatments with properly enhancing process to finishing. That's the concept. That's the theoretical concept as referenced in the book of Raymond and Colwick of the Material Handling Handbook, page 99-100. So basically I started with this raw material, as you see in this bottom, and had done some cutting and profile milling, and cut those red portions of the piece with a hole with a drilling, end up with this piece that I'm looking for my design. And that's here a summary also that I have also provided, showing the NC programming and the steps clockwise, starting from as per the way it has been presented to us in our class. So basically it's a wheel bracket process plan. It starts with a concept part, and then we apply the CAD program according to the code of of NC programming we use, and we apply the CREO manufacturing and the cutter path as discussed in the homework series that we have discussed in this class. So I will not spend time on how to to do this NC programming, which was also detailed in the profile. This is part of the program. This is not the full program. This is just a snapshot of the profile milling and drilling used for this bracket, and all, of course, supporting files are provided. So now manufacturing in a simple format. This is the sheet we provide to the shop. It shows the process plan for the profile milling and the drilling here, as you see in this table, with the diameters and the twist drill and the time taken. This is called a process plan sheet that is usually used to show what type of manufacturing processes we applied and time taken per minute. Here's another something I have done for this design is I basically showed how the load is being applied for this semi-electric stacker. If you remember, this is the stacker that we showed in the beginning of this presentation. I made a drawing for it. There's a load applied, which here's where the load comes, and this is it's usually done and referenced in many products that are in the market. And there's something called the maximum. It's like a self weight of the electric stacker that is 1,000. That is assumed 1,000. We have a payload. We have a wheel center distance, and that's what the distance from here. I see this arrow from the load that is on the basically applied on the stacker. We will be able to do some load analysis. Why I am doing this? I just wanted to feel and sense the new design, because you see on this photo here, I have this new bracket manufactured. I have less bolts, number of bolts. I have a casted bearing bush here, some load applied to it. I want to know what's the difference when the load is applied to this new redesigned compared to the actual design. I wanted to make sure that the new design is handling the loads properly and avoiding some of the problems that were brought to us by the survey. Because this wheel, as you can see, the nature of this load and how the load is being distributed here, which can only be observed through some finite element CREO simulation, which is not part of our course, but it's just something I was able to do some extra reading on, related to the CREO manufacturing, and trying to see how the load is applied and distributed and transmitted from, because if the load is not in the right position or the bracket is not designed right, this will cause more wear and failure to this wheel. And that's one of the issues that we have already a problem in the industry. So basically what I did here, and this is just one sheet I have done it. This is not, it's just something extra. I felt it will be very nice to show. I was able to just to test the CREO simulation, which is to basically try to use the same, to look at the redesigned wheel bracket with this casted bearing, and I tried to apply load and stress. Basically it's like a finite element analysis here that shows with my new design. You see how the circles of stress are transmitting towards this plate here. So it's like uniformly going through, because you see the shape of this bracket has contributed. So we apply, see there's here a series of load. We apply from very low to very high, and we show how the stress is being compared to what? Compared to the actual design. Look to the actual design. It's different. You see here, it's circles going through. It's like all going towards the plate. So when you apply a load on that, where the load pin, the load pin will be coming here through these two holes, and here's the actual design, and you see how it's drifting to the right. I was able to reach to this conclusion, which is in the actual design we notice that the stress is more concentrated near the hole, like as I showed you, and it's basically shifting to the side instead of going towards the top plate. So this what the saying, it's like you see the shifting of this stress, it's shifting to the side while it's supposed to go where? to the top, because that's where it's more, because if that shifting to the right, will cause more wear to the wheel and failure. So basically what I'm saying here, that in the actual design we notice the stress is more concentrated near the hole, and its path is shifted to the side instead of going towards the top plate of the bush, which is not healthy, and it's not a healthy load distribution, and of course as a result there will be excessive wheel wear. But on the other hand, the redesigned manufactured bracket, we notice that the stress path is going towards the top plate of the bearing, which is good and encourages more product life, which is we have seen in this design. You see this here, the loads are being shifted towards the plate instead of shifting to the side, causing more wheel to the wear. So what do we conclude from this? And this is as I have mentioned, it's excessive time done trying to put these parts and assemblies together, that we have found that the design for assembly and design for manufacturing applied in our case for that semi-electric stacker have really inserted some concurrent engineering. And you know, this concurrent engineering is a terminology we use in system engineering, which is really important, and it provides collaborative context. What do I mean by this? What I mean by that is that the new steering system that has been developed is basically is helping us to basically re-engineer. I understand that the part that we have used for this project, something that you may see so many kinds in the market, but this is a unique semi-electric stacker that is usually mostly applied in grocery warehouses and some up to 3,000 pound load applied to this, compared, it's like a middle range. So my point is that the design for manufacturing and the design for assembly applied has really showed to us some really like immediate engineering response, meaning whatever we do in terms of manufacturing changes or reducing the number of parts, we can sense the impact immediately. So we have faster, easier level of control because of the less number of parts, and because of the way we have done the design to make it easier for assembly, investment allocations, and effective process planning, because the process planning here is much less complicated. There is a smooth transition also that we have, as you have seen. I have showed you the parts designed. I was able to move through the process from design process to manufacturing very easily and very smoothly, and I'm sure you have seen that, because the plates, the type that I have designed it, the way I have done the process into manufacturing, there wasn't much of a complication. So the redesigned saved us many repetitions. We didn't have to create a prototype and test, because it's all simple and to the point. Fewer parts and assembly line, of course, I have done and reduced. So we have much less fasteners, pre-assembled features, self-positioning also of parts, and casted parts in place of a weldment assembly. So we have much less cost in the welding, much material reliability instead of having 3 parts welded together. So we have reduced the assembly time by 39% compared to the whole assembly cost by 15%. So we have reduction in cost and reduction in time of assembly. And cost usually is as a result of the manufacturing, because less machining, less operations, less labor. You will not need more people to work, more effective logistics also, because we have avoided material sourcing from more than one supplier. We just know what we want. We went and did. By the way, I will show you now that I did not try to manufacture every single part. There are some existing standard parts that I was considering to be part of something that we buy, but I am only talking about there are some assembly and manufacturing design done, but the rest are some parts that I was able to buy from the market for much cheaper. So design for manufacturing and design for manufacturing in this product re-engineered and has reduced absolutely the unit cost, much shorter lead time from the time we start working on the raw material to the delivery. I found the lead time, which is to be ready to be delivered to the customer, it's much less, and that was shown in the many tables discussed before. So we have increased the reliability of the products, because casted parts not with less welding will make it more reliable and more safer, and actually the safety factor. One of the reasons that people usually go for design for manufacturing assembly, sometimes they look to the part that exists in the market and they want to re-engineer it. So we do some re-engineering in order to fulfill some requirements, company requirements. For example, this stacker, when was originally created by a very good Chinese company, but what happened, the design in the Chinese company is not really accounting for much of a safety. Like usually the safety factor doesn't go more than 0.9 or 1.0 compared to 2.0 in our design, and that was all also assumptions made in the calculations. Here's a summary sheet for the project. How did I distribute my time for these projects? I divided the projects when I started into 4 sections: actual steering, which is the actual existing steering concept design as outlaid in the brochure of some companies; actual steering design, the same actual design I have created the CREO files, the part files and assembly sub-assemblies, and then I defined the parts that are going to apply manufacturing and assembly, and I have done the drilling and milling operations for the CREO, for the wheel bracket. And the total hours spent into this was about 162 hours. These 162 hours took me about 2 months and 1 week. I started February 20th. Since the first day Dr. Zhu have posted the projects, and ended just with the presentation file these days. So it's about 2 months and 1 week. Before I would like to show you here something. Also in this file, I have shown here the steering system actual design. If you see here, I have created the part numbers INN 53501. All the parts I have for every single, for these 3 parts, which is the left hand assembly, the right hand, the pivot pin, and I have showed the quantity that I need and the manufactured versus bought product. So as you see, not every one I have manufactured. The ball bearing, there's some standard products in the market for ball bearing and truss bearing, and this is the specification for these bearings that I was. So the ones that are being manufactured are some side plates, which is the wheel plates. There are some bottom plates that I can save money on manufacture, but the truss bearing here, again, I bought it. The pivot lock I put. So I have showed all the standard parts, and that's provided also in my report. Basically, I would like to thank you so much for giving me the chance to present this project, and it will be, of course, more and more useful if I was able also to show some these CREO files, and how basically was to give more time on the design. I wanted you to also, if you have time and you have some time, to look at also some video that I am posting. I have posted also on YouTube for a recent logo that I have designed and developed for our industrial engineering departments as part of the bonus projects offered by Dr. Zhu. And at the end, I would like to thank you so much and I will be more than happy to answer any questions via the discussion groups that Dr. Zhu has created over Blackboard. And also, you can leave your comments and feedback on anything that you see, because I will provide a link. It's called like an instructor link that can help you basically provide any feedback on anything that you have seen. I would like to thank you again for your time, and I wish you all the best in your projects. My name is Nidal Alsayyed. Again, LT0380624, a doctoral student at the Industrial Engineering Department. You have a beautiful day. Thank you.